The multimeter is an absolutely fundamental tool for anyone interested in electronics. To listen to some people on the internet, you'd think you'd have to spend hundreds if not thousands of pounds to get a high quality multimeter to meet all of your needs. But in fact, that isn't really the case. And I'm going to look at some cheaper multimeters here today and why you don't need to spend that sort of money. And for most purposes, even the cheapest meter on this bench here today, which costs £3.50, will do the job for you. Now, I'm not saying you should necessarily go down that route, but you don't have to spend an arm and a leg to get something that is very usable for most electronic purposes. If we think about a beginner in electronics, or someone who just wants a general purpose meter for simple stuff, or we think about someone who is strapped for cash, you want a meter that's good enough that fits a budget, and that's what these three meters here are all about. This one's here because I've had it for a ridiculously long amount of time, and I want to make the point that for a long period I used this, and I used something called a Maplin Gold, which is essentially the same as this, just packaged slightly differently, and etc, etc, but roughly the same. And I don't know how old I was, 20 or something like that, when I invested in my first digital multimeter, and and these served perfectly well for a very, very long period of time. Let's look at the two outside ones. So this is a 6.5 digit meter which is being calibrated, and it's ridiculously accurate, and I'm going to use that as a benchmark for everything else. So that's why that's there. It's not that I want to review it or talk about it particularly, it's just a stupidly accurate meter that will enable us to look and just see how well these perform. So that's why it's there. This one's there because it's a real meter that I've used for a long time, and sometimes even on my videos today you will see this meter appearing, just because actually it's got very large digits, it's nice and clear. I do have this meter which I use on quite a lot of videos, so to buy one of these new, you're looking at, I don't know, what are you looking at actually, $600, something like that, £500, something in that region, maybe a bit more depending where you buy it from and how well you have it calibrated when you buy it. I got this second hand actually and did a repair on it, so I didn't spend that much, and I've been able to cross calibrate with this, because this is a 4.5 digit meter, this is a 6.5 digit meter, and this is 2 magnitudes more accurate than this is supposed to be. So I can actually use this as a calibration transfer standard. So this has been NIST standard calibrated, so it has known uncertainties, etc, etc. I can therefore use that to check this meter, and this meter is perfectly fine. So anyway, what have we got on the bench that we are going to look at? So let me move this out of the way first of all. So if we think about a beginner, or even someone who's been doing quite a bit of electronics, so a lot of people do, for example, stuff with Arduinos and PIC microcontrollers and Atmels and stuff like that. Some people might be doing some analog electronics, amplifiers, LEDs, stuff, that type of thing. Maybe looking at some switch mode power supplies, so that's a bit higher voltage and that sort of thing. But we're covering sort of that sort of ground, maybe some RF stuff. But again, you're really just going to be measuring the voltages on transistors and ICs and that sort of stuff. So most of what you do is what, within 30 volts, 0 to 30 volts, plus minus. Occasionally you might need to measure the mains, let's say. You might need to measure some higher consumption. If you're working with motors, then you'll need some higher current. But generally speaking, 3 or 5 amps is the maximum you're going to go up to in current terms, and whatever your mains voltage is in your country in terms of AC voltage, and in DC voltage it would be rare to be up above, let's say, 40 volts. Now for electronics, you often see, so for example, a meter like this one, that will tell you, the headline figure will be, oh, it goes up to 10 amps. Fantastic. Actually, that matters less for electronics. What you want to know is, what does it go down to in amps? So if I look on the amp DC, This one goes down to 2 milliamps. So in other words, 19999 would be what you could get on that display. So 1.999 milliamps. So those right-hand digits are microamps, of course. Now, essentially, forget about the last digit, because the last digit, by the nature of a digital multimeter, is going to be rounded. And let's say, for example, you're reading 1 microamp. Well, that is the right-hand digit here. So you can forget about reading, you know, serious microamp, low microamp readings, because, you know, it could be 2 or it could be 3. Well, what does that mean in terms of microamps? Well, it's pretty imprecise. Who knows? So ideally, you want to go as low as you can in the current range, because, you know, on standby, a PIC microcontroller, for example, might be, let's say, 20 microamps. So yeah, you know, you want to measure that sort of stuff. Okay, let's move this one out of the way. Remember to turn it off, which is what I normally forget. And focus on these. So what's the price range that I've got here? So one of them is beeping because it's about to auto power off. £3.50. This one was less than £10. And this one was the more expensive of them, which is £20. But you can see this is a full 4-digit multimeter here. It probably doesn't read 4. It's probably going to be a 3 or a 6 in this left-hand digit here. Auto ranging, manually ranging. So this was £3.50. Now this isn't from eBay, and this was bought from CPC Farnell. This was bought from CPC Farnell, and so was this. This is Multicomp, this is Duratool, this is Duratool, and yeah, so those are the prices. They all come with leads. The cat rating that you see on things relates to the environment in which you're using the equipment, really. So a Cat 4, we're talking about things like automotive, HVACs, air conditioning units, maybe outside, that sort of stuff. Here is a Cat 4 600 volt probe from Keysight with all of its correct markings on it, and on the back it says Cat 4 and it's doubly insulated, and that will have features like if you scuff the insulation, there will be a different coloured insulation inside, so it shows through, and the same with the leads. These will be multicoloured internals on the leads as well, and these ones actually plug together. They're quite nice. But notice the tip, it's all shrouded up to about, you know, 3 millimeters from the end. Let's say this guy. It's very common for them to come with a little clip on like this. So this is a 10 amp lead. Without that, it is Cat 2 only. So Cat 2 is simple, like domestic testing, that type of thing. If I put this on, boom, now it's Cat 3 1000 volts, Cat 4 600 volts. This is a 10 amp cable, which matches the 10 amps for the meter that it's attached to. So yeah, the leads do matter, and ideally you want a longish lead, let's say 900 millimeters, 3 foot, and you want sharp probe points. You can sharpen them, it's not a problem. You will lose, of course, the plating that's on it. If you do, ideally they could do being gold plated or stainless, but yeah, you're paying more for those. So sharp as possible, really, and ideally with these insulators, certainly if you plan to use them automotive or outside or on main circuits or anything like that, you should have these little insulating sleeves. And you want them to be flexible. This isn't terribly flexible. You can see it's got bends in it, whereas there you go. This is the Keysight one, which is like, you know, just flexible silicon, beautiful. Yeah, all the top ones will be silicon. Now, these are not silicon, but they're getting close on this guy here. And yeah, this one also comes with some. It's not these clips. This one also comes with some covers to up the cat rating. So it's only Cat 2 without a cover. So yeah, these are slightly sharper. So overall, the quality of the probe, pretty crappy, but you can get away with it. Okay-ish, you can get away with it. Not too bad. I'm going to do some performance tests on these now. And what I'm going to do to begin with is I'm just going to plug them all in parallel to the same power supply, which unfortunately is going to make a bit of noise, which is a bit annoying. Then I will do a similar test where I measure some current, and then we'll look at the input impedance, and finally I'll do a little thing on a breadboard to just discuss where some of the readings might go awry. So I have connected up my power supply through onto this copper bus bar just here and this one just here. So these are just lengths of copper that I've cleaned, and the reason is that I want each meter to be connected through some leads to kind of a common plus voltage point and a common 0 volt point. That way they're not kind of chaining through a series of connectors. Each connector could lose some voltage, etc, etc. So let's just get each one on DC volts. So I've set this one to 20 volts because it's manual ranging, and these are just set to volt DC, and this one's set to volt DC as well. And I'm going to just center up these meters a little bit more in the display. Excellent. So let's take a look at this, and we'll improve the accuracy of this a shade just so we're dead on. So we can see that it's 4.999 and a bit. So MPLC, which is the power line filtering essentially. So I'm going to switch that down to 10. And we can see that instantly this has become a lot more stable. So 4.9994, and then we've just kind of got a little bit of movement in the end there. Okay, let's have a look and see what all the other meters think. So this guy is the cheapest at £3 something, 4.96, nearly 4.97 occasionally. So the error on this guy is 0.7%. That's all. So if we think about a 5 volt regulator in, let's say a 7805 general purpose regulator that we might use in, let's say, a digital circuit at 5 volts, that's probably only, well, I don't know, 1%, 2%, 5% maybe. So this is easily capable of reading your 5 volt rail and telling you that you're close enough. When you see a lot of the repair videos, you'll see us probing the power rails. And we'll probe a 5 volt rail and it'll read 5.1 and say, yeah, that's all right. Gives you a feel for what you're actually working with there. You look at a 12 volt rail, 12.2 volts, yeah, that's fine, absolutely fine, not a problem at all. If it was 4.9, we'd say, yeah, that's all right. So there is tolerance to be thought about. And generally speaking, unless we're working with really, really high expensive equipment, then the tolerance isn't really that important. It's when we're actually calibrating that we need something like this. Now we can see the voltage is actually shifting a little bit, and there's two reasons for that. One is that I haven't had this turned on for all that long. It's only been on for about half an hour. And the other is the power supply has only just been turned on, so it's not going to be perfectly regulating. So this value will change a fraction as we move along. So this guy here, the middle guy, 5 volts, 5.00 volts. So I can't really actually measure the error on that, because if I took this to 3 digits, it would read 5.00. Okay, and the final one over here, 5.013. So I can do, yeah, 0.2% error on that one. So yeah, nothing essentially, yeah, essentially no error on that one at all. Let's wind it up to 10 volts. So I'm not going to go through the palaver of looking at every single measurement with you on this. We can see here we've got 9.94, 10.01 and 10.0. So these are all pretty much on the money again. Even the 9.94 is that's within 0.6%, so no big deal really. Okay, so let's turn this up to 12 volts now, because 12 volts is a value you would use quite a lot. We quite often test 12 volts and 15 volts, but just 12 will do. So here we go, 11.93, 12.02 and 12.0. So what can you say really? They're all pretty close to the actual reading that we've got on the Keithley. Okay, so changed it to 50 volts. And this is quite interesting because this enables us to show the benefit of that 6,000 count on the right hand meter. So if we look at the two left hand ones, 49.6 and 50.0, so that's fine, the accuracy is okay. But if we look at the right hand one, that's 50.07, 50.08, we have an entire additional digit of precision on that. So when we talk about plus minus 3 digits, for example, on the last digit, yeah, that makes a big difference. So I think that's about it for voltages. We could go and look at some AC voltages and mains voltage and stuff like that, but I don't really see the point. Essentially, other than the fact that it's going to be rectified, and the right hand one's got true RMS, whereas the others are probably averaging. You know, we're not really going to see a lot of difference, just slightly less accuracy. What I am interested in, though, I've made a big point about ensuring that you get something with current measurement on it. So I'm going to set up some experiment now so that we can just have a look and compare the current measuring capabilities of these. Okay, so I've got these set up for reading current now. So essentially the plus comes in here and it goes into the milliamp input on this, comes out the common into the milliamp input on this one, out the common into the milliamp input on this one, out the common and into the milliamp input in this one, and then it comes out the common in here and goes up to the load, which is drawing, it's programmed to draw 50 milliamps, but it's actually drawing 49.2. And this kind of illustrates the thing that we're to some degree talking about. So that's the current load is programmed for 50 milliamps. It says it is drawing 48, but in actual fact it's drawing 49. So that means it's one digit off in what it's reading, just to the which is, you know, 1 milliamp. So it's got a 4-digit display on the current load. So even the current load, which is several hundred pounds, the last digit can often be wrong. The last digit on these is always kind of questionable. You can never really trust it. It's always like plus minus 1 at best, and if you look at the spec it could be plus minus 5, all sorts of things. And the same on this one. This right hand digit is rounded in some way. So anyway, we've got 49.29, 49.2, 49.545-ish, and 49.31. So these are all, so that's only got an error of what, you know, 10, 20 microamps, a little bit more on this one, and yeah, this one's reading a little bit under. So, you know, but only by a few microamps here and there, not a lot to worry about. So there's something to point out here, which is this one here, which is £20. That is resolving an extra digit, and that's because it can use its left hand digit to read, I think, up to 6 on this particular one. So yeah, they're all 3.5 digit multimeters, but this one's left hand digit can go an awful lot higher. So when you're buying these, do look at the actual count, not just the number of digits. So yeah, so if we now increase this, then let's just wind it up a little bit and see how they behave. So this one is on its 200 milliamp setting. So let's not wind it up, let's wind it down. So I'm not quite sure how low I can persuade this to go. Okay, I reckon that's about it. So 26.7 microamps. So we'll turn this on to 2000 microamps and we can see it's reading 26 microamps. Pretty bloody good. Turn this one down to microamps. 26.7. 26.7. Well, 26.8, okay. Microamps. 26.6. So even right down at those ridiculously low currents, I mean 26, 27 microamps is nothing. You know, could you go lower than that? Probably, but I'd have to set up some different test gear in order to do it. So yeah, let's turn these up and go higher, and let's see what happens, I suppose, as well if we overload. So I'm going to now go for 0.199. Okay, so I've asked for 199 milliamps and I'm getting 198.87, 199.2, pretty good, 199.78. So this one actually is overreading by about a milliamp, which is nothing much. It's only 0.5% error. 198.7. And it should be 198.8. So yeah, that's a tiny error, 100 microamps error. That's all. So nothing much at all error-wise on that, 0.1% or something. So really accurate. So the reason I chose 199 is to put these right close to what I think will be the cut-off limit for this one. So I just want to see what happens if we push that current up too high. Oh, there we go. So both of these can only have a 1 in the left-hand digit, and both of them are attempting to display a 2. This one's just kind of showing an error display. This one's showing OL for overload. So that's fairly straightforward. So we can move this plug from the milliamps across to the amps, would be how to solve that. Thank you very much. There we go. Right, okay, cool. So now we're in the amps connection. Yeah, we can read them all, I think, on the screen. Just avoiding reflections there. So this one loses quite a lot of resolution. So 0.19. This one is doing 0.199. So, you know, you can see kind of the price difference coming into effect there, and this one's still reading 199.5 because it can go a lot higher. And we should now be able to wind it up quite easy. And we'll see what happens when this guy overloads. So 291, 0.28, 291. So yeah, you see the limitations of this really cheap one now. But here's the thing. So 300 milliamps, 290 milliamps is what you're reading on this one. So 301.8 milliamps, 301 milliamps, 301.6, 290. So this isn't about accuracy, this is about the precision of the readout. But we do see, I think, why we pay more for each one along the line. So all 3.5 digit meters, but the actual precision we get out of them varies. So I'm going to try and get this as close as I can to 500. 500.5. Yeah, which is that. I do have another digit I could play with, I suppose. There we go. So this is as close as I can get to 500 milliamps, 0.5 amps. So, 0.49 amps. 498 milliamps. 499.8. So, you know, really, really good. £20. You'd have difficulty getting change out of £1,000 for this guy. Now, admittedly, this is more accurate. But really, do you need to be that accurate for most things? For repairing equipment, that's fine. You know, for building circuits yourself, that's fine. For all of that stuff, that's fine. For calibrating other meters, oh yeah, I'm going to need something like this. For making a piece of test equipment that's 0.01% accurate, I'd better go for something like this. But usually, this guy will be fine. And this guy, you know, you're paying the money for other things as well. It's networkable, it has graphing functions and all sorts of stuff. So I wanted to show one of the issues that can occur when reading voltages with a multimeter. Now, I'm exaggerating the values here so that they so the problem shows up clearly. But be aware that this is always present. And if, for example, you've got a moving coil meter, then it will be present a lot of the time. So this guy here is set to measure voltage, and it's in auto range and things like that. Now I'm going to do something with this, which is I'm going to grab one of the other meters, if I can find it. There we go, this guy. I'm going to use this to measure what the input resistance is on this, because everything has an input impedance or input resistance. I'm dealing with DC, so I'll call it resistance for argument's sake. So okay, so this has got, I've got it set to a 10 mega ohm input impedance, and there we go, here's our well, 9.9910 ish. This isn't going to be that accurate at the top end of its resistance. Auto on here, and now this can't read it, and that's because this has got stupidly high input impedance. It kind of, I think it's a gig ohm, so it's 1,000 mega ohm input impedance is capable of switching to. Anyway, let's pull those out. But most meters, and certainly all these handheld meters, will have a 10 mega ohm input impedance. So what does that mean? Well, on this circuit, I have 70 volts coming in, and that's across two 10 mega ohm resistors. So I would expect to read 35 volts across each resistor. So let's measure it. Let's put the probes right around in my hands. So across this first resistor then, 23 volts. What? Across the second resistor, 23 volts. And I promise you, I've got 70 volts across there. I want to measure across the two, I get 69 volts. What? Well, there is a 70, 69.98. So there's my 70 volts. But if I measure halfway, I get 23.3. Measure the other one, 23.3. So that's 46, 47 volts. If I add the two together, 47 volts, not 70 volts. So what's happening? Well, first of all, the 70 volts is reading correctly because it's coming from a regulated power supply. So despite the fact that I'm connecting my multimeter's 10 mega ohms across the 20 mega ohms here, I've still got that voltage present. All that's happening is I'm drawing a bit more current, that's all. However, when I join it across here, then this 10 mega ohm resistor is now in parallel with the 10 mega ohm in the meter. So that's now 5 mega ohms in that part of the circuit. So I've got a 5 mega ohm and a 10 mega ohm. So I would be then looking at a third of the voltage at that point, and yeah, 23.3 times 3. So the presence of the meter across that resistor is changing the voltage across that resistor, and it's really changing the voltage across that resistor. If this was in a circuit we were measuring, the circuit behavior would change because I've connected my meter across there. Now, I'm using 10 megohm resistors here to highlight the problem and make it really, really obvious. However, if I used a 1 megohm resistor, that would be 1 meg in parallel with 10 meg, and there will still be an appreciable change, just, you know, a tenth of the magnitude that we just saw there, really. But actually that would still be a few volts difference. So 23, I mean, we're losing a massive amount of voltage there. Now, if this was a moving coil meter, the input impedance to the meter might be something more like 10k, 20k, maybe 100k. Now, 10 megohm resistors are pretty rare in a circuit. 10 megohm input impedances are not rare in circuits. But 100k and 10k, I mean, they're all over the place. You'll find them everywhere. And, you know, stick a 10k or even a 20k or 100k moving coil meter across one of these, and you'd have virtually no reading there at all. And the resistor, this 10 megohm resistor, or let's say 100k megohm resistor, will reduce in value to a little bit less than whatever the meter's impedance is. So if you have 10k impedance on your meter, a 10k resistor, you've got 5k, nothing really. If you've got 100k on your circuit and you measure it with a 10k meter, then you've probably got about 9.5k or something like that. That 100k has vanished essentially in your circuit. So this is why you want the highest input impedance you can possibly get, and all these digital meters will have a 10 megohm input impedance typically, but you should read that in the spec. But hopefully that illustrates the problem. Now you get a similar problem when you're measuring current. So I'm going to put this onto a current range. Let's put it onto microamps. And let's measure what resistance it has on that. So if you remember, I said that when we measure current, then essentially across the two connections it puts a resistor, so the current flows through that resistor, and then it measures the voltage drop across the resistor. So what is the resistor that this guy puts in for microamps? So let's go to ohms on here, so two-way ohms. I can't really join these together to zero them, but anyway, so we'll just plug them in. We'll plug this one in here. There it is. So 100.8 ohms. So it's probably a little bit lower than that. There'll be a little bit of resistance in these cables that I haven't zeroed out. But it'd be a 100 ohm resistor on that microamp range. So I'm interested to try something here. Let me just try this guy. Unfortunately, I can't use these probes with him. So this is something called a microcurrent gold, which is an addition you might want to use for your meter. And its job is essentially to reduce the resistance. So I've put this into its microamp range, and on it, it tells me the resistor that's in there is a 10 ohm. So hopefully it is. Gosh, this is one stiff cable. These have been designed not to pull out. Okay, so this time I can actually zero it. So there we go, point. So it's just auto zero, that's near enough. Current input, there we go. 9.96 ohms. Well, 9.97 ohms to be honest. So there we go, that's the input in the, so that's 10 times lower. So does it really matter? Well, it depends how much current is flowing through that resistor, doesn't it? So if we're at the sort of top end of the range, then there's a reasonable amount of current flowing through it, and there'll be a reasonable amount of voltage drop actually occurring. So let's say, for example, we've got a 3-volt little coin cell battery that's powering a low current circuit, and we pop in, let's say, this meter to measure the current that's being used. Then we've put 100 ohms in series with the power supply, basically. And so yeah, that might actually drop a fair bit, but probably not a huge amount. So let's say that it's doing 1 milliamp, or 500 microamps. There we go. So 500 microamps times 100 ohms, and then we divide that by 1,000,000, because it's microamps, and we get 0.05 volts. So 50 millivolts drop. Is 50 millivolts drop relevant? Well, it might be. So for example, if this battery, you want to measure how this battery performs as it discharges, then that 50 millivolts starts making a lot of difference. The battery only starts at 3 volts. If you've got a 1.5 volt battery, it matters even more. So what would it be on this one? Well, the answer would be 5 millivolts instead of 50 millivolts. So that's why a few people have these. So these are microcurrent golds from EEV blog. And you can either get the circuits and build it yourself because it's open source, or you can order one from EEV blog. If you don't want to modify it, I would suggest you buy it from EEV blog, because he designed it, give him the benefit of a few pounds here and there, and he tests them and calibrates them and all the rest to make, say calibrates, he ensures they are within calibrated range, which is 0.1%, I think. So there we have it. Hopefully you found that useful. Hopefully that's perhaps convinced you definitely shouldn't buy a moving coil meter from eBay or Amazon, and also giving you some information to help you evaluate what meter would be good for you, particularly as a starting meter. There is a little question, which is, should you buy 2 multimeters? So for example, the green one and the middle one here would be pretty decent choices, but we've got all 3 meters here. They all did a pretty reasonable job. I think personally that the little one just has a few too many limitations. It's the sort of thing you throw in a toolbox, not use as a useful tool on your bench. And I think you outgrow it even as a beginner in electronics fairly quickly. The green one would be my choice, to be perfectly honest, and I'm pretty happy to use that. And in fact, I've used it on a few repair videos already. I would encourage you to get the data sheets of your kind of contender multimeters, pore over them, check the burden voltages, check the resistors that they've got in series, check that you've got a full 10 meg ohms, check that you've got low current ranges, as many digits as you possibly can, and not just the number of digits but the actual count that it goes to. Yeah, other than that, I'll put the links in for these, but as I say, I'm not specifically recommending them, but I think they're pretty good value for money. At least the 2 right-hand ones are. So anyway, if you enjoyed that, please give it a thumbs up, like it, leave some comments down below, of course, and yeah, subscribe if you haven't already done so. See you later. Bye now.